Lecture 34 is in large part a review for exam 3, though I do want to continue talking about the topics from last time, projectile motion, this time with air resistance, and then talk about the data science, the data modeling with density functions and cumulative distribution functions again, and re-emphasize the main things there. The formulas, once again, with the projectile motion are going to be pretty complicated, but I want you to just focus on the main ideas. I might ask you conceptual questions related to these ideas. The calculations sometimes are just too nasty. So here we go. We use Mathematica as well. So this is the same example as before, as last Friday. The projectile is fired out of the launcher. Here's my launcher. It made it look like a little cannon here. With an initial speed of 500 meters per second, at a 30-degree angle from the horizontal, pretend this is the ground, and so this is a little bit underground. Model the motion of the projectile with parametric equations. Assume, again, for simplicity, that the mouth of the launcher is at ground level and put it at the origin of the coordinate system. Choosing your coordinate system appropriately helps keep the equations simpler than they would be otherwise. Another simplification is to start time at 0, though in theory we could start time other spots as well. This vector, this red arrow, is the velocity vector. Its length is 500. And so using trigonometry in this right triangle, the fact that this angle is 30 degrees, which is pi over 6 radians, you can figure out the length of the adjacent side to this angle and also the length of that opposite side. For example, the cosine of this angle, cosine of 30 degrees would be, think about SOHCAH, C-A-H. Cosine is adjacent over hypotenuse. So whatever that is, if I call it xa initially, x divided by 500 would have to be the cosine of 30 degrees, which is square root of 3 over 2. And so you can solve for x and you can get this. Right? Those are called the horizontal and vertical components of velocity. I'm not testing you on the vectors themselves, but I think it's good information to know about for the future. But let's be more realistic this time. Last Friday, we were being less realistic and only assuming the force of gravity. But now we're going to include air resistance. That does make the model more complicated, but more accurate. There's always trade-offs in modeling. If you want extra accuracy, it needs to be more complicated. But hopefully a computer can still handle analyzing. Now you've got to consider Newton's laws more carefully. We really didn't consider Newton's laws last Friday. I didn't really think about F equals ma. It's Newton's second law. I will think about it now. It's because we really only need to think about it in the vertical direction last Friday, and we had already done that like a month ago. So now we need to think more carefully. I'm not using the letters F and G for the functions here, because the reason is because G is I'm going to want to reserve for the acceleration due to gravity. So I'm calling them just x of t and y of t. This is technically abuse of notation, but it is a common thing for people to do. Again, there's two forces now, gravity and air resistance. Gravity is still a constant force pointing straight downward toward the Earth. Air resistance is a non-constant force, actually. It points in the opposite direction as the velocity vector. We can draw the general picture here. So you fire the projectile, it's maybe right about there at a certain moment in time. The force due to gravity, I like making little half arrows, but you can make a full arrow above the vector if you like. F grav is pointing straight down. It's a negative scalar multiple of j hat. J hat points straight up. And the scalar in front of it is actually not negative g. It's technically negative mg. If I got rid of the m, that would be the acceleration due to gravity. Putting the m there is necessary if you want the actual force. So that all objects have the same acceleration due to gravity, you need to put the mass there as well. The size, the mass of the object does affect the force it feels from the gravity of the Earth. The velocity vector would look about like this. Remember, I've said the velocity vector points in the direction of motion at any instant in time. It's tangent to the curve at whatever point you happen to be at. It does move with the curve. It does change both direction and length. And its length equals the speed. When it gets longer, that means the motion's faster. If it's shorter, the motion's slower. The force due to air resistance has to be a negative multiple of that. It's got to point in the exactly opposite direction. This would be the force due to air resistance. The total net force would be the sum of these two forces. And without explaining why, the way you figure out what the sum is you make a little parallelogram here, where this side is essentially the same as the force due to gravity, and this side, if you draw an arrow that way, is essentially the same as the air resistance. Pretend that's a parallelogram there. And the total force turns out to be the arrow or vector that starts here and points at the other side of that parallelogram. It's called the parallelogram law. That's the total force, F sub tot, or total. It's the sum of the force due to gravity and the force due to air resistance as a vector. Okay? And so that has a definite effect on the motion. Newton's second law turns out to be is F equals ma, where A is a vector as well as F. That's still true in vector form, it turns out. So like I just told you, it's simplest to assume that this air resistance is proportional to the velocity vector. So, and with a negative constant proportionality. So, not only it points in the opposite direction, but it's proportional. As the velocity vector gets longer, so does the force due to air resistance. If the object's traveling faster, the air resistance is greater at a proportional amount. If you double the length of the velocity vector, you double the length of the air resistance. Is that the most accurate possible model? Not necessarily. It actually depends on the shape of the object too, okay, and its density and that kind of thing. You know, a feather shot out of a cannon is going to act differently than a cannonball shot out of a cannon. Again, the total net force is the sum of the two forces. There's the force due to gravity. Here's the force due to air resistance in symbolic form. A negative constant times the velocity vector. And it is proportional to the velocity vector then, with a negative constant proportionality, which again means it points in the opposite direction. You could write that in terms of the components of the velocity vector. It's common to write, say, the velocity vector as v sub x times I hat plus v sub y times j hat. Those are functions of t, by the way. You could also write this using the notation on the screen as x prime of t times I hat plus y prime of t times j hat. Where x and y, those functions of t, are giving you the coordinates of the point, which are also the components of the vector. So now I add those two things to get the total force. You group together the two j hat terms, this one and this one, into one term like this. And this is a symbolic way to represent the total force. What do you do with this? You use Newton's second law, F equals ma, to write this. There's the ma, which is the same as m times the derivative of the velocity. It equals this. How does that help? Helpful. It's really a differential equation in disguise. In fact, it's what's called a system of differential equations. You can take this one vector equation and write it as a system of two scalar equations. If you focus on the I hat parts, and there's implicitly an I hat part on this side, the derivative of v with respect to t. On the board here, if you want to move the camera to the board here, is this. Take the derivatives of the components of the velocity vector, that is the acceleration vector. If you equate the I hat term there with this I hat term, it gives you this first equation. I also divided both sides by m. And if you equate the j hat term on this side with this j hat term, you get this other equation. Again, I divided both sides by m. That's a system of differential equations for two unknown functions, vx and vy. Is it easy to solve? Well, it's not the hardest differential equation to solve. It's possible. I did use technology to solve it, and I'll show you what I got here in a few minutes. Why do you want to do that? What do you want to do with it? If you can solve this system of differential equations, here's the most important conceptual point. It gives you the velocity vector as a function of time. And therefore, if you integrate that vector, it's going to give you the position vector as a function of time. In other words, it's really going to give you x of t and y of t. We want to solve for those functions. We want to know what those functions are. That can help us answer all sorts of questions, like how long is the projectile in the air? When does it hit the ground? What's the highest point? What's the speed? What's the distance traveled along the curve? That can. The answers do depend on all these parameters, the k, the m, and the g. Of course, g near the surface of the Earth is 9.8 meters per second squared, but if you were on the moon, it would be different. Or if you were on the top of a mountain, it would be different. Or if you were on Mars, it would be different. G is dependent on the size of the planet or moon, and also how high above the surface that you are. M is the mass. It can be different for different masses. K is related to air resistance. It's different depending on whether you're shooting a feather or a cannonball, for example. And again, it's not absolutely clear that it's accurate in all situations. It's just the simplest kind of thing to try next. Turns out the velocity is this. Okay? So the formulas get complicated now. And the point is not to necessarily write down the formulas. Okay? They get complicated. The more important thing is just to understand the overall big picture, the ideas. And to appreciate the fact that we can actually solve it. You can find formulas. You can even do this by hand, but it's certainly nicer with technology, and I'll show you that. It's also worth noting, when you look at this, to see the exponential decay in it. When you bring in air resistance, the velocity involves an exponential decay. There and there. That's something new from the no air resistance situation. And as t increases, what happens to exponential decays? They go to 0. So as t increases here, the I hat component of the velocity goes towards 0. So the velocity vector becomes, well, in the long run, it actually becomes more vertical, going straight down, actually. This part goes to 0 as well, leaving just that part when t is large. Negative mgk times j hat, yeah, close to pointing straight down when t is large. You can integrate to get the position. That's even more complicated. Don't write it down. Could you do this integral if you had to? Well, it would be definitely very tricky. Maybe if you had to, based on the knowledge that you have. If you had enough time, and if you had to, and you weren't feeling too stressed about it, you could do it based on the knowledge you have now. For example, integrating a constant with respect to t gives you that constant times t. Integrating something like e to the negative k over m times t, just think of it as an indefinite integral. It's got to still involve an e to the negative k over m times t. It's got to involve that still, right? Because you know how that's the way integrals and derivatives with respect to exponential functions behave. But if you just leave this and put a plus c there, that's not quite good enough. Because if you differentiate this, the chain rule gives you an extra factor of negative k over m, which you do not see in front of you. So you got to compensate for that, and the way to compensate for that is to multiply by negative m over k. Then when you do the chain rule, everything cancels to give you a 1 in front. You differentiate. You see a negative m over k. Well, it's in there, but it's sort of in disguised form in a different place, a few different places. We do need this position vector to go through 0 when t is 0. So I can't just put a plus c, which means I have to figure out what c is. And through a bunch of complicated calculations, both of these things are equal to 0 when t is 0. E to the 0 is 1, you get a 1 minus 1 is 0. Same thing happens here, you get a 0 there, you get a 0 there. When t is 0, this whole thing is 0, you are at the origin at time 0. What's the speed? The speed is always This is definitely something to know for the exam. The square root of x prime of t squared plus y prime of t squared. Or if you prefer Leibniz notation, you could write dx dt, quantity squared, plus dy dt quantity squared. That's what the speed is. It's the length of the velocity vector by the Pythagorean theorem. And so I need to take that velocity vector up there in red and put it in a square root after, like that. Nasty, okay? But still doable. Okay. And again, it's nice to get the computer to do this for you, so you don't have to figure it out. What kind of function will that be? What kind of graph will it have? Well, I hope it makes intuitive sense that because of air resistance, the speed will continually, for the most part at least, decrease, unless it's a small amount of air resistance. So it's going to start relatively high, well, in fact, at 500. It's going to go down. If the air resistance is real low, very little air resistance, it'll probably go back up now as the cannonball, say, heads back toward the ground. But if there's a lot of air resistance, like with the feather, it's probably going to keep going down. So depending on what k is, the graph of the speed versus time is going to look like one of these things. This is small k, and this would be large k. But either way you do it, the integral of the speed is still the distance traveled. The area under the curve is still the distance traveled. That's the fundamental theorem of calculus right there. That turns out to be true. No matter which situation you're in. And that kind of function is always increasing because as I move this point to the right, call that t, again I'm abusing notation here. As I move that point to the right, I get more and more area, no matter whether the speed is increasing or decreasing. So the distance function is always going up. Concave down at first, and maybe well, it's either going to look like this or this. This is the case in small k, and this is the case for large k. But it's always still going to be going up. It's not going to be going back down again until you hit the ground. Yeah, the distance is still an integral. Oh boy, I don't want to do that integral. Could somebody pay me to do it? I guess so. Would I have to be successful? I'm not sure. That looks so complicated. I don't know that I could do it. Can Mathematica do it? I tried yesterday. Okay? I was amazed it worked. So here we're being thankful for technology. We can praise God for technology. I know technology is often frustrating. It's frustrating to me sometimes too. By the way, here's where I had Mathematica solve the difference equation. With certain initial conditions, there's your initial velocity in the x direction, and here's your initial velocity in the y direction. There's the velocity vector, really. You can actually integrate the velocity vector to find the position vector. That works. And in fact, you can do it as a definite integral. That's where I got the formula for the position vector. Just had Mathematica do it for me. Then I can enter those functions into Mathematica and figure out the speed. I will figure out the speed in a minute, but I want to show you something else first. Maybe zoom in on this if you need to here. I did try to figure out the time when it hits the ground by solving for where y is 0. And I got an answer, but it's a weird answer. Blah, 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 blah. Product log? What's product log? It's just a function you've never heard of before, that's all. That is the moment in time when it hits the ground. And you can plug in numbers into it. So for example, when the mass is 10 kilograms, the K is 0.1. What would the units of K be? I think they're units of force divided by units of velocity. So k with units would be newtons per meter per second. What does that mean? I don't really know. It's just units. It doesn't have a ton of meaning, other than just to make things work out right. And there's g is 9.8. If that's the case, it takes 47.3 seconds to hit the ground. This model predicts. So if you want to know if the model is accurate, that's probably the best thing to try. Shoot it, see if it takes 47.3 seconds to hit the ground. But remember, it travels kind of far. So what happens if k increases, like 0.2 instead of 0.1? More air resistance. It probably won't be in the air as long. This number here should go down. Yep. And if k is really big, 20 is pretty low. Okay, let's get extreme here. Okay, too small. All right, too small to represent a normalized machine number, so I guess I can't do that. And even though I don't know what product log is really, I can still plug it into Mathematica and like evaluate it at different spots and make an animation showing the trajectory. So there's the trajectory. There is air resistance here, k is 0.1. And we see some vectors in there. The blue vector is the position vector. The red vector is actually not the velocity vector, but I scaled it up to make it longer so you can see it. And these other vectors are the forces scaled up higher than they actually are, so you can actually see them. The orangish one is gravity, the brown one is air resistance, and the pink one is their sum, the total net force. And if I increase k, watch what happens. Ready? 1, 2, 3, go. Increasing k, right? It doesn't travel as far. Isn't that cool? And it's definitely no longer a parabola. I mean, if k is positive, it's definitely not a parabola, but it's more extreme if it gets larger. What if gravity gets larger? Then it doesn't stay in the air as long either. What if m is larger? Then it actually does stay in the air longer. It goes further if the mass gets bigger, according to this model. How about speed and distance traveled? Could I figure those things out? Yeah, but it was good I didn't have to do it by hand. I had Mathematica do it for me. There's the speed. I plug it in there. There it is. Integrating that, this thing will give me the what? That's the speed. Integrating it will give me what? Come on, you guys know it. We've been doing it over and over again. Integrating the speed gives you the distance. Yeah. With a plus c in there, we have to pick an appropriate c. And believe it or not, Mathematica did it. Here was the most surprising one. It did it. That's the distance traveled up to a constant. Yikes, I don't want to do that by hand. Hey, there's our old friend, arctangent. Well, I guess we did arcsinch before, didn't we? Inverse hyperbolic tangent. Yeah, that h is supposed to be there, actually. Inch. See? Does this go through the origin? It actually does not. There's its value when t is 0. So I actually had to subtract this off from it. And I got this nasty thing. That's the distance traveled. And I can plug numbers in and find out how far I went along the curve. When m is 10, k is 0.1, and g is 9.8, and I plug in 47.3 seconds, which is how long it's in the air, it travels along the curve this many meters, which is about 17.5 kilometers along the curve. I'm just jumping for joy. To me, this is just so much fun. It's amazing. It works. I don't want to do it by hand, but I can have the computer do it. Mathematica is pretty amazing. And I can plot these things and get graphs, and I can change k and so forth with the distance and speed. Yeah, the k is low. The graph over on the right for the speed. Actually, these are both graphs of the speed and distance traveled. But it's easier to see the one on the right for k, just so you can actually see the graph easier. If k is small, then the graph definitely goes up. If k is larger, okay, it looks like it still does speed up as it hits the ground, but just barely. On the right, this is slightly positive slope still. Okay. So I want you to see the big ideas, and just be thankful that you can get the computer to do it for you. Let's also talk about the big ideas with the density functions again. Mind you, the key concepts with the density functions. Let's look first at that normal curve example. I'm not going to show you the data this time. I'm just going to think about the functions. A normal density function is an important kind of function. It's got kind of a complicated formula. I don't expect you to know that formula for the test. That's the density function for a normal curve. That's a function whose graph looks like this. Yeah, you do not need to put this on Unicode. Okay, if you need it on the test, I'll give it to you. Graph is a bell-shaped curve. It's centered on this number called mu, which represents the mean of the curve. It's really the center of mass. By symmetry, it's got to be where the peak is. And this thing called the standard deviation measures the horizontal distance between the peak and the inflection points on either side. So this number right here is mu plus sigma, and this number right here is mu minus sigma. What should you be able to do with this on a test, for example? You should be able to verify that there's global max at mu and inflection points at these other points. How? By taking derivatives and setting them equal to 0 and so on. Correct? And with the critical point, show you've got a local max either with the first or second derivative test. That's not enough to prove it's a global max, but it is. The graph definitely goes lower when x moves away from mu. I mean, that should make intuitive sense just looking at the formula anyway. That exponent of v is a negative quantity. It's going to be 0 when x is equal to mu. So you get v to 0, which is 1. If x is not mu, then that exponent is a negative number. E to a negative number is less than 1. It's got to be smaller when x is not mu. You can just think about the function as well to verify it's really a global max. You know, maybe I tell you sigma is 1 and mu is 2 or something, so the formula would simplify to this. If mu is 2 and sigma is 1. And maybe, you know, as far as finding derivatives go, well, and setting them equal to 0, I mean, you've got this constant out in front. To make things simpler, you could just call it c for constant. Interesting that it involves pi. You might wonder why would it involve pi. Let's see these circles here. That's an aha kind of mystery in math. Why would that involve pi? So you should be able to differentiate this. A function c e to the negative x minus 2 squared over 2. You need the chain rule. You get c e to the negative x minus 2 quantity squared over 2 times the derivative of this top. And the derivative of that would be, you don't actually have to expand this out, you can use the chain rule again effectively. Bring the 2 down in front, subtract 1 from the exponent, don't forget to divide by 2 there, and then multiply times the derivative of the inside function, which is just 1 because the derivative of x minus 2 is 1. That would be the derivative. Setting this equal to 0 and solving for x gives you only one possibility for x, because this is never 0 here. E to the power is never 0. C is not 0. This has got to be 0 for this entire thing to be 0, and that's going to mean x is equal to 2. And that will be a local max. That is the location of the peak. For the second derivative, to find the inflection points, you'd have to differentiate this, which would involve the product rule as well as the chain rule. That's something that's worth practicing for the test. Even with an arbitrary mean signal. What about the CDF, the cumulative distribution function? Remember the DF, the density function, just represents the density of the data. The data is going to be denser where the graph is higher and less dense where it's lower. You have lots of data in here, relatively speaking, close to mu. The CDF is how you find the percent of data less than a given number. And you can even write this kind of equation. This is probably worth writing in your note card. Capital F of x, the CDF, cumulative distribution function, is the percent of data less than or equal to x. Approximately. These are models. Or you could actually think of it as a probability as well. It's the probability that the next data point will be less than or equal to whatever x is. It's an antiderivative of little a. The derivative of the CDF is the density. But it's not any old antiderivative. If your density starts at 0, for example, you want capital F of 0 to be 0. We saw graphs that look like this last Friday. That's not what happens actually with the normal distribution, because x can be anything. You actually have to modify the CDF formula a little bit with the integral. This formula does work. And it applies, for example, when x is mu. You get an integral from mu to mu here, which is 0. There's no area under the graph when you're just above one number. Plus 1/2 is 1/2. And what this means is that for this example, if mu is right here, the graph of the CDF has got to go through the point mu comma 1/2. That's what that means. Because of the fact that when you plug in mu equals x equals mu into here, you get an integral from mu to mu, which is 0. Plus 1/2 is 1/2. And that's saying half the data is less than the mean. Which makes sense if you come over to this picture with the camera. Half the data would be less than the mean by the symmetry. Half the area is to the left of the mean. That's another way to think of it. It's a complicated integral, and oh, by the way, there's a typo here. That should be a fraction there. So complicated, in fact, that nobody can do it. There is no simple formula for this. Nobody can do it. But it can still be approximated, like with Riemann sums and graphed. If you do approximating rectangles for the area, and you do it and make them skinny enough, have enough of them, it's going to be real close to the true value for any particular x. And you can graph it, and again, it does look about like this. You should be able to conceptually understand that if you, for example, want to find, if mu happens to be, say, 5 or something, and you want to find the percent of the data less than 4, the way you do that is you go up to the graph of capital F. And over here, and maybe the answer is 0.23 or something. And that would say 23% of the data is less than or equal to 4. You should understand that concept right there. That's essentially what I erased there. Okay. You can actually differentiate this integral with the FDC. Think about it here just with me. Taking the derivative of this is actually easy, because the derivative of 1/2 is just 0. The derivative of this integral, where the variable's up there, is just this function. The answer is little f of x when you differentiate this. Even though it looks difficult, it's actually very easy. The derivative of an integral like this, where the true variable you're after is up there. This is the thing in the book called the second fundamental theorem of calculus, or the antiderivative construction theorem. It looks hard, but it's actually easy. It equals little f. Put an x in there. These need to match. Don't put a u. Don't put an a. Those two numbers need to match, or those two letters need to match. When you differentiate the accumulated area, you get the function back that you're finding the area on. If this is little f of x, or think of it as f of u, and this is a particular value of x, this integral here represents this area, if a is 0, say. Differentiating that function at that value of x gives you the second coordinate of this function, of the original function. That's what it's saying. And the higher that second coordinate is, the higher the derivative is, meaning area is being accumulated faster. That should make intuitive sense. If the graph is higher as x increases, the area is going to grow faster than if the graph is low. This area will grow faster than a graph, the area under a graph that looks like that, as x increases. These are really important things. Very subtle, not easy to get your mind around, but it is the heart of what calculus was when it was discovered. Newton and Leibniz discovered the fundamental theorem of calculus. That's why we say they are the creators of calculus. Methods for tangent finding, optimization methods, and methods for finding certain special areas existed before the fundamental theorem of calculus. But the fundamental theorem of calculus ties them together and allows you to solve many, many more problems than you would otherwise. We might want to show the limiting value of this function is 1 as x goes to infinity. That's pretty hard, actually. It requires multivariable calculus. We're not going to do it. I did just happen to get a video in my YouTube feed, though, where somebody does that. They verify those as well. I want to talk about the gamma distribution, but we're getting low on time here. Because I wanted to talk about L'Hopital's a little more. Let's go through our general review, and if we have time at the end, we'll come back to this slide. So here's our general review of the topic step. Where do we start? Essentially at the end of chapter 3, which is the theorem section. Theorems and their applications. That really wasn't the very first thing that we did after exam 2. The very first thing we did after exam 2 was the optimization with the soup can, or yeah, to minimize the surface area for a given volume. But as we went through that problem-solving process and other kinds of problems, we talked about the theorems as well. So what kind of theorems are we talking about here? We're talking about the mean value theorem, MVT. As we go here, and maybe you're writing this stuff down, you should take a few seconds to think about it. The MVT. Visually, what did that mean? You got a nice function, continuous and differentiable, say. There's some point C between A and B where the slope of the tangent is the same as the slope of C. Again, it looks about like that. Right about here or so, the tangent line is parallel to that. It has the same slope. So the C would be this. F prime of C equals F of B minus F of A divided by B minus A. The mean value theorem can be used to prove the increasing and decreasing function theorems and also the constant function theorem. The increasing function theorem proof we did. It was one of those proofs I said was really subtle. I wouldn't expect you to know it. But from scratch, but you should go back in your notes and think about it. It's one of those proofs I said where if I gave you blanks, you should be able to fill in the blanks with reasons. So you should understand it, even if you don't do it from scratch. There was the racetrack principle. The racetrack principle can be used to prove by the mean value theorem as well. I won't write down the symbols for it, the words, but intuitively, at least there were 2 bullet points for it. The first bullet point said, if you got 2 horses, say, that start at the same place and at the same time, that the horse that's always faster will always be ahead. Seems really, in a sense, kind of dumb. Of course that's true, but to prove it mathematically requires the mean value theorem. So it's something that seems obvious, but it still requires proof. You did have some homework problems where you used the racetrack principle to do a proof, and in fact, if you look at one of the old exams, I have a proof, or 2, maybe one on each exam, where the racetrack principle is needed. We did an example in class. We proved, if I remember correctly, that the square root of 1 plus x is less than or equal to 1 plus 1/2 x for x greater than or equal to 0. We proved that in class. Should you be able to do such a proof from scratch? Probably not from scratch, but if you look at the old exams, at least it's on one of them, I got them started on the proof. And I just had to finish it. So that's something to practice. I think this one I also gave an example to you. I wrote out one. Kind of a pain to use in a sense, but it is something you should look at. First and second derivative tests. You should understand the meaning visually, but you should also be able to apply them. And I really haven't emphasized this as much as I'd like to, but if you're applying the first derivative test, it's good to make a number line and mark off the points that are critical points. Maybe there's 3 of them at A, B, and C. And then look at the sign, positive or negative, of the derivative in these 4 intervals that the 3 numbers have broken the number line up into. Maybe f prime is positive over here, negative over here, positive over here, and maybe positive over here. It didn't change sign there. That can happen. F prime of C is 0, but just to the left of C and just to the right of C, f prime is strictly positive. What would the graph look like in such a situation? Something about like this. This is not lining up perfectly, but get the idea? So if f prime changes sign from positive to negative, as it does at A, you draw a picture, you can see it's got to be a local max. It's like a little hilltop. If f prime changes sign from negative to positive, as you pass through B, it's got to be a local min, like a little valley. And if f prime doesn't change sign, which can happen as you pass through a critical point, then it's neither a local max nor a local min. This is a critical point right there. The tangent line is horizontal. I'm trying to imply it's horizontal by how I'm drawing it. But it's not a local max or a local min. That can happen. The simplest example is x cubed. Right? So there's a visual description of something that can happen. But you should also be able to apply this with a particular function. And the old exams have examples. I think there's one example on both old exams. What about the second derivative test? You plug the critical points into the second derivative. You'll get a negative second derivative there because the graph's concave down. And that will imply it's a local max at this critical point. You'll get a positive second derivative here, implying that at B you get a local min. What about there? The second derivative there won't be positive or negative. It'll be 0. It's an inflection point, in fact. The concavity changes from negative to positive. So the second derivative test doesn't tell you anything there. And in fact, it's neither a local maximum. If the second derivative is 0, does that mean it's definitely neither a local maximum or min? Actually, that's not true. F of x equals x to the 4th power is very flat near the origin, so flat in fact that its second derivative is 0 there. F prime of x is 4x cubed. F double prime of x is 12x squared. That means f double prime of 0 is 0. 0 is a critical point. And it actually is a local min. In fact, global min for x to the 4th. But the second derivative test tells you nothing because it equals 0. It's just so flat here. That's the reason the concavity essentially is 0 there. The first derivative test does tell you it's a local min, because the first derivative changes sign from negative to positive. There are situations where the first derivative test applies, but the second one doesn't. That's the simplest example. We talked briefly about the extreme value theorem. You got a continuous function on a closed interval. It's got to have a global max or global min. Got to have a high point and a low point. If your interval's not closed, it doesn't have to have a higher low point. For example, if the interval is just the interval from, say, the open interval from 0 to 1, don't include the endpoints, and the function is, f of x equals x plus 1, a nice simple function whose graph would look like this, that actually doesn't have a global max or min. Really? Wouldn't the global max be 2 and the global min be 1? No. Because there's no number strictly between 0 and 1 whose output equals 1 or 2. You can get arbitrarily close to those outputs, but never equal to them on this domain. 1.2 does equal 1.9 repeating. They're equal. But if you stop the 9 somewhere, maybe you put a billion 9s and then stop, that doesn't equal 2. The function does reach 1.9 with a billion 9s, but it doesn't reach 1.9 with infinitely many 9s. Very subtle things here. Another example is, say, f of x equals 1 over x. Same interval here, open interval from 0 to 1. The graph looks like this, and it's got a vertical asymptote at 0. It doesn't have a global max, because it goes up forever and ever. You might say that should mean infinity is its global max, but no, infinity is not a number, and it never reaches infinity. It just gets arbitrarily large. It gets above any horizontal line. Methods of optimization with, you always want to find the critical points. Take the derivative, set it equal to 0, solve for x. If you're after local extreme points, then you use either the first or second derivative test, maybe in conjunction with graphing the function just to be sure. It's possible, like I just mentioned over here, for a critical point to not be a local extreme point. Move the camera over here, please. It's possible for a critical point to be neither local max or min. For global extreme points over closed intervals, you have to also check the endpoints. Compare the values of the functions at the critical points and at the endpoints. Which output is highest, which output is lowest. The output that's highest is the global max value, also called the best upper bound. The output that's the lowest is called the global min value, also called the best lower bound. In this picture, if I fill in the circles, make a closed interval, then the function does reach 1 and 2, and it does have a global maximum. Global min of 1 at 0, and global max of 2 at 1. If you fill in those missing points. Also be able to find inflection points using the second derivative. What do? You find the second derivative, you set it equal to 0 and solve for x. Technically speaking, the second derivative needs to change sign at an inflection point. Graph has to go from concave up to concave down. or concave down to concave up. That means the second derivative changes sign. But I'm not going to make a big deal out of that as far as solving problems. Solving problems, it will change sign. Coming back to this picture over here, this is an example where the second derivative does not change sign at the place where it's 0. There's actually no inflection point at the origin. Stop me if you want something clarified. I know we're going fast, but we have to because of time. Maybe we can take questions if you have them. And be able to think about this purely graphically, like we've been doing already.
Just to clarify, you said that for inflection points it has to change sign in the second derivative graph.
The second derivative has to change sign.
In that graph. The second derivative.
This is the original graph. This is f.
Oh, okay.
Here f is concave up, so f double prime would be positive. Here is concave down, so f double prime would be negative. F double prime changes sign there. This is f as well for a different f. It's concave down there, f double prime would be negative. It's concave up over here, f double prime would be positive. It's changing sign. F double prime is changing sign.
But it changes concavity in the
original function. Functions with parameters, families of functions. Be able to deal with this? 1 or 2 parameters. There's an old exam question, for example, where the parameter, I believe, was called b or something like that. And I think the function is like this or something. And you're trying to figure out how the inflection point, or the critical point depends on b. And the critical point is the local max. It might have been x squared there, I forgot. The graph looks something like this. And the coordinates of this point depend on b. This is something I really emphasized a lot in the context of the soup can example. You should be able to figure out how the critical point, say x sub crit, depends on b, and how the maximum value here, call it y sub max, how does that depend on b as well? Sensitivity analysis then differentiates these functions with respect to b to see how fast these things change as b changes. There's a lot of terminology as well. I try to give you some help sometimes on these exams. I give you some guidance. They're kind of high-level ideas. And the pressure of an exam, it's hard to think of them. So something like this sometimes I'm going to give you some guidance, at least as far as like the sensitivity analysis. What are you after? What am I after? Another important kind of example in families of functions is differential equations and their solutions. Be able to check whether a function solves a differential equation or not. Right? Here's a differential equation, here's a function. How do you know if it's a solution or not? It's the left-hand side, right-hand side thing, right? You plug the function into the left-hand side and simplify, and you plug the function into the right-hand side of the differential equation and simplify. As a simple example, maybe f of x is 1 over 1 minus x, and the differential equation is dy dx equals y squared. Is this function a solution to that? Well, what does the left-hand side simplify? The left-hand side of the differential equation is dy dx, the derivative. So I need to find the derivative. I could use the quotient rule. I could also realize this function is 1 minus x to the negative 1 power. Use the chain rule. Bring the negative 1 down, subtract 1 from the exponent, negative 1 minus 1 is negative 2, multiply times the derivative of 1 minus x. I'm not trying to solve for this as 0, I'm just trying to simplify it. This simplifies to 1 over 1 minus x quantity squared. And the right-hand side of the differential equation is the y squared. When you plug in the function, that means replace y with the function. I need to figure out f of x squared. Get that? You plug it into the right-hand side, you plug it in place of y, which means you need to take the function and square it. That's the trickiest part. That's y squared. Y equals f of x. So I get this, but hey, that's the same as this. And lo and behold, these are the same. It's like magic. It's not magic, I just knew the answer ahead of time. That's why I've done enough that I know the answer ahead of time. These are the same, so that means this function is a solution. I won't have you graph slope fields, but if I do give you a graph of a slope field, you should be able to graph the function in the slope field. In this case, the slope field looks something like this. These slope marks get higher and higher as y gets higher and higher. And this function here, if you graph it, looks about like this, and it does follow the slope field. Anytime it passes through the midpoint of one of those line segments, that line segment will be a tangent. Because the differential equation says I'm looking for a function whose slopes at every point equal the y-coordinate squared of that. And I make these slope marks to have, for any given y-coordinate, for example, the slope there would be the square of the y-coordinate. 5 squared in that case, or 25. Make a slope field that you should review too. But I'm not going to actually have you make slope fields for the exam. Our models were exponential growth decay, Newton's law of cooling and heating, and the logistic model. If I had you do this, probably I'd give you some help. I'd give you the formulas for these things. But you should be able, if I give you the formulas, you should be able to check that they solve the differential equation, for example. Although the logistic one is kind of nasty to check. And be able to solve for the unknown constants if I give you some initial conditions, like let's say cooling coffee, maybe y of 0 is 50 degrees Celsius or something, and you're trying to use that initial condition to figure out the formula. We did talk about that. Problem solving, optimization and related rates. Be able to do an optimization problem similar to one of your completion assignments, homework problems, and same with related rates. Now you can make really nasty optimization and related rates problems that are really hard. I keep the simpler examples. You know, I for the most part assign simpler examples than I could have. Just want you to have the basic idea, and certainly for exams, simple examples are typically the better way to go. It's easy to make mistakes, it's easy to get confused, so I'm going to make it similar to completion homework problems for both of those. L'Hopital's rule, you know, we didn't spend a ton of time on that. I'd probably give you guidance if I give you a L'Hopital's rule problem. There are examples on the old exams, at least one of them. And on my answers, I tell you what to do. So you should look at those and try to remember what I verbally said last week about that. Know when not to use it as well. It's got to be one of those indeterminate forms. Either 0 over 0 or infinity over infinity are the examples we considered. There are actually others. And if it does not satisfy one of those, you do not want to use it. In one of the old exams, there's a problem where you do not use it. The function is continuous, so you would actually just plug in the number. It's even simpler than multiplication. Parametric equations, curves in motion. Understand what they are, how to graph them, be able to graph them on your calculator. Probably I won't have you actually plot points, but you should be able to use your calculator to either draw them from scratch or just to help you feel confident in your answers. Be able to find the speed function and maybe optimize it if asked to. So it's easier to optimize the square of the speed. When I say optimize, I mean either maximize or minimize. And be able to find when the tangent line to the parametric curve is horizontal or vertical. One of the completion homework problems was related to this one that was similar to this here. We did that example in class. There was one completion problem that was kind of tricky that way. You know, I would avoid extra tricky ones. The tangent line is going to be horizontal when dy dt is 0. And it'll be vertical when dft is 0. That's the main things to know. Typically. If they're both 0 at the same time, that's when strange things happen. But relate this stuff with integrals in the FTC. Distance traveled is an antiderivative of the speed, but you need to choose the plus c correctly, so that dist of a is 0, where a is your starting time. Often 0, but it doesn't have to be. And you can represent it as a definite integral. And the FTC implies that the distance is also the area of the curve. It's the essence of the FTC. One more slide here. Before I go on to that slide, let me just think about the fluid flow example. If R of t, for example, like on the quiz, this might be on the quiz 10 instead of quiz 9, is a flow rate, say in liters per minute, and time is in minutes, you can imagine this product to be in liters. And if dt is an infinitesimal amount of time, then this is an infinitesimal volume. You can call this dv. When you integrate, it's like you're adding those up to get the total change in volume. The change in volume is the integral of R of t dt over whatever time interval you happen to be talking about from A to B in general. It's another way to think about the FTC. And since R here in general could be positive or negative, having a net inflow versus a net outflow, this integral could be positive or negative. And to find its value, or to think about its value, you have to take these areas as positive areas and subtract this area, if you think of that area as positive. If this is A1, this is A2, and this is A3, then the value of the integral is going to be A1 minus A2 plus A3, where I'm considering each of these A's to be positive numbers. You can subtract A2 because the graph is below the axis. So we've already talked about these to some degree. Evaluating definite integrals, you have to find an antiderivative, right? A capital F. Capital F of B minus capital F of A. Just talked about those things. Other applications includes volume flow rates, also position and velocity compared to distance and speed. I'm talking about one-dimensional motion there, where you might be going back and forth. And then finally, applications and approximations. There are a few other properties. These come up in the quiz in section 5.4 to read about. I talked about them it was either last lecture or the lecture before that. These linearity properties and intervals properties. I know that's very fast because we have only a finite amount of time, and I think the other stuff is important to really bring things to a close. Don't forget to do the course evaluations. I'll send you a reminder. It's due by Wednesday. I'll send you notes if I think of anything else. Okay? Office hours are usual tomorrow, but you can stop by any time.